So here now, so we learned how we calculate theoretically how we calculate the asymptotic variance, and especially how we can incorporate the first stage error in the second stage standard error. Now we are going to think about the implementation. So theory is theory, but when you write a code, when you write your own code like program, it's still very confusing what you have to do, and even if you did wrong and you know what you may know it is wrong, but it is hard to see what is wrong. So I'd like to compare the typically wrong formulas used in many papers by students. So now, so imagine a software like say, so I'm going to consider generic notation. Dependent variable is A and independent variable is B. So when you type regress A on B on Stata, Excel, MATLAB, or whatever program you have, the program returns this OLS estimator, right? This is the OLS estimator, B prime inverse, B A. And then, and of course, the program will calculate the fitted value. F hat is denoted as the fitted value for the dependent variable. Fitted value is calculated as B prime beta hat. So beta hat is this much. B prime beta hat is the fitted value. And the residual is A minus B prime beta hat. Right? This is the residual, estimated residual. Okay, so I intentionally use totally different notation just to make it kind of exotic, just to refresh your mind. And so, okay, it is straightforward. Then finally, we are interested in the variance, how the program calculates the variance, which is basically the standard error. So the variance will be calculated for the OLS. If you use the OLS variance will be calculated this way. So remember, sigma squared expected x prime inverse. That was the OLS variance, asymptotic variance, and the program calculates the variance in this way. Sigma squared is calculated using the residual squared summation, and then x prime expectation inverse is simple, just sample average of regressors and take inverse. This is so far I described what the program calculates for you, what the program could calculate for you. Now let's think about now. So this is the OLS, and let's see what happens if you use the same OLS program for the two-stage least squares. First, think about this. So this is, now we are coming back to our original notation, y and x. So if you think about a regression of y on x, this is exactly what we learned, and simple. So you are going to get beta hat this way, and variance of the estimator will be calculated by variance of the OLS error term and x prime. So epsilon is calculated this way, and so epsilon is calculated this way. So this is the built-in program, built-in code. So it does not consider instrument, it is just a benchmark. Now let's compare. Like, so in the next step, you'd like to implement the two-stage least square. So what you can do there is, you first use the OLS program, OLS function, to estimate the fitted value of x2, endogenous variable. The fitted value w hat can be calculated using this formula. The fitted value formula is built in. That is not a problem. That's good. That's fine. But then after you get the fitted values, you may want to use the OLS function again. Y is regressed on the fitted value using the OLS method. That is typical mistake. Then let's see what you get. So your estimator will be calculated this way. You regressed y on w hat, then y w hat, the regress y on w hat will give you this beta hat, which is correct. Beta hat is correct. But the problem is the variance. The variance will be based on this residual. The residual is y minus w hat beta hat, right? Because you regressed y on w hat. This is your residual, and using this residual, the variance is calculated and x prime inverse is calculated. So this is what you are going to get. Now, and it is wrong. It is not what you want. This was wrong because this part is wrong. What you have to calculate is, so beta hat is correct. There is no problem in beta hat, but this part should be defined again. So the residual, in particular the residual that you use in the variance calculation should be written in this way. So you are not, so even if your regression is y on w, but the residual is calculated based on x. That is the main difference, right? So it is, we only need epsilon, not u. So u includes epsilon plus beta psi, but beta psi part is cancelled out by the first stage errors. So this is what you have to do, but you need to write a new code if there is no two-stage least square function on your program. But anyhow, so you have to see the differences between the simple OLS and applying OLS twice without adjusting for the first stage estimation. And third is the correct method. So this is, so the idea is the regression, the residual, how you calculate the residual is different from what the regressor you use in the regression estimate. That's the main point. And this is why where many students and many even researchers make mistakes. Okay, so this is like exactly this is what I explained. So you need to calculate, you need to observe the difference between these two guys. And interestingly, the variance can be ordered. The variance can be ordered under general, like under some assumptions, but usually variance of u is greater than variance of epsilon. So this is the correct variance, but you may get this in general in many cases. Okay, and then finally, I will show you that the optimal GMM is equivalent to the two-stage least square estimator. Like, or you may think it as just a matrix notation approach to the optimal GMM, right? So we are going to analyze the GMM estimator using the matrix notation. It should be simple. So moment condition was written this way, and rewrite this in this way. Summation can be simplified by like so z, capital Z prime y minus x beta, and weighting matrix was given by this. Also, it can be simplified to z, capital Z prime z, and 1 over n inside the inverse can go outside as n. And then given this weighting function and this moment condition, the criterion function is moment function prime weight moment function, which is like this. So this prime, this times this again, and we have this And you have a very familiar thing here. Exactly, this is the projection matrix. So like now you see the similarities, and you need to minimize this. By the way, 1 over n does not matter in this minimization. So it is just a constant. So if you take the first order condition of this criterion function, also differentiate with respect to beta. There is one beta, there is another beta. So actually there should be 2 in front of this. You have to multiply 2 here, but it will be cancelled out by dividing by 2 on both sides. 2 will be gone, and 1 over n will be gone for the same reason. So you have this equals to 0. And then beta hat can be written in this way. So like rearrange the terms, and then projection matrix is here. Exactly, this is what you get in the end. And this is what we had from the two-stage least squares. So it's an interesting result. We learned 2 different methods to estimate the regression model with an instrumental variable, but the 2 methods are the same. And so in general, by the way, in general, I would recommend to use the GMM method, because GMM method is more general. So the least squares estimate, two-stage least square method works only when you have like linear regression in the first and the second stages, and everything should be clean. But the GMM method can be applied to different applications. Even if the function is nonlinear, it's not a problem. Even if the moment conditions are nonlinear, not a problem. Or so GMM method can be applied to general cases. Even your model is like not a regression model, still GMM works. So pay more attention to the GMM, and when you have a chance in the future in your dissertation, like usually the GMM would may work for your paper. Almost in any case, GMM would be the most likely candidate for your estimation problem in the future. Okay, this is the end of chapter 4, and I will post homework 4 that corresponds to this chapter. And as I said, you have to do the algebra by yourself. And chapter 5, now we are going to chapter 5, which is about the hypothesis testing. And I think, so last year, usually my problem is going too fast, but somehow this year I don't have enough time. I think I don't have enough time to finish what I did last year. So in my calculation, we have 7 more lectures, 7 more classes. So my plan is hypothesis testing for maybe like 2 or 3 classes, and then simultaneous equations model and the quantile regression model. This is my goal. Like I would like to finish these 3 more chapters. Yeah, so I will do my best to finish that. Last year I did 1 more chapter after quantile regression, but I think that is not possible this year. Okay, and good luck, and see you later. I will continue to chapter 5.